First question states, name with reasons 3 other angles equal to x. We name with reasons 3 other angles equal to x. Thank you. Because TAB is a tangent to the bigger circle, so angle A2 will be equals to x according to tan chord theorem. Let me write it down. The first angle will then be angle A2 will then be equals to x. Where is A2? This here is A2. It means this angle is also x according to tan chord theorem. Tan chord theorem. A2 is equals to x. That is the first angle. The question states name with reasons 3 other angles equals to x. So we already have the first one, it's A2. The second one, the second angle equals to x. We have x here, we also have x here. If you look at A2 and A5, there is a relationship. Those are the vertically opposite angles. And vertically opposite angles are always equal. Therefore, it means angle A5. Angle A5 is equals to angle A2. And I remember A2 is also equals to x. Why do I say A5 is equals to A2? Because those are the vertically opposite angles. Those are the vertically opposite angles. So we go to A5. You mark it x as well. A5 is also equals to x. So the question says name with reason 3 other angles. Look at A5. Look at P2. It means A5 will also be equals to P2 according to tan chord theorem. The third theorem will then be P2, angle P2 is also equals to A5. And remember, A5 is equals to x. So it means P2 is also equals to x. What is the reason for that statement? Why do I say A5 is equals to A2? The reason is the tan chord theorem. Tan chord theorem. So those are the 3 angles equal to x from that diagram. Thank you. Did you get them right? But it's very much interesting. Let's go to the next section, the second part of the question, which states, prove that APTR is a cyclic quad. Prove that APTR is a cyclic quad. We have 3 ways of proving a quad to be cyclic. There are 3 ways of proving a quad to be cyclic. Number 1, if the exterior angle of a triangle is equal to the interior opposite, if the exterior angle of a quadrilateral is equals to the interior opposite angle, then the quadrilateral becomes cyclic. Secondly, if the opposite angles of a quadrilateral are supplementary, then it means that quadrilateral is also cyclic. So, thirdly, if the angles subtended by the same side of a quadrilateral are equal, if those angles subtended by the same side are equal at the vertex, therefore it means that quadrilateral is also cyclic. Those are the 3 ways of proving a quad to be cyclic. So you need to think hard and analyze the problem and see which way will be more appropriate this time. And every time the question says prove, when you are required to prove, I always say ask your question when. When whatever it is that you are required to prove will be true. Ask yourself a question when. For instance, if I have to prove that APTR is a cyclic quad, ask yourself a question when. When will APTR be a cyclic quad? You've got quite a number of possibilities. It can be if R2 is equal to P1, exterior angle, interior opposite angles. Or if you can say, you see P3 plus P2, if they can be equal to R1, that is a possibility. Or if R1 plus P1 is equal to 180 degrees. Those are the possibilities. So if you look down, you analyze and see what you have, then you work on what you have mostly. Look at the information that you have and then look at the part that is more relevant to the given information. So when answering this question, when will APTR be a cyclic quad? When will APTR be a cyclic quad? If we can prove that angle R2 is equals to angle P1. Now we have a direction. Now we have a direction. If R2 can be equals to P1, then we can prove that. Let's work towards that. Thank you. Proof. Then you ask yourself a question, when? So that you should have a direction. You must know I'm working towards achieving this objective, towards reaching this destination. Prove that APTR is a cyclic quad. The question is, when will APTR be a cyclic quad? And the answer is, if R2 can be equals to P1. Now we start looking for angles that are equals to P1 and those that are equals to R2. Let's start. Already P1 is equals to A3 from the information that TP and TA are tangents. So we start. A1, P1 is equals to A3. That's the statement. We are now at 4.2 now. 4.2. P1 is equals to A3. Think of the reason. See, because PT is equals to AT. That's the reason. PT is equals to AT. And that is according to a theorem that states tangents drawn from the same point. Tangents drawn from same point outside the circle. Those are the tangents drawn from the same point outside the circle. In full, the theorem states tangents drawn from the same point outside the circle are equal in length. That is how we say PT is equals to AT. PT is equals to AT. Because those are the tangents drawn from the same point outside the circle. Look at A3 and A6. What is the relationship? Vertically opposite angles. Therefore, A3 is also equals to A6. Those are the vertically opposite angles. Vertically opposite angles. Look at A3, look at A6. I'll mark them equal. All the angles that I'm marking, they will be equal. Remember I said P1, I marked it like this, is equals to A3. Now A3 is equals to A6. Those are the vertically opposite angles. I've marked them the same. All those angles are equal. It means P1 is equals to angle A3 is equals to angle A6. Now check the relation between angle A6 and R2. Angle A6 and R2. Tan chord. Thank you. Therefore it means A6. Angle A6 is also equals to angle R2. That is according to tan chord theorem. Tan chord theorem. All the angles that I've marked are now equal. It means R2 also I must mark it exactly the same. Mark it like that. All those angles are equal. P1 is equals to A3 and A3 is equals to A6 and A6 is also equals to R2. I have been providing reasons all along. So all those angles are equal. What does that mean? Therefore means we conclude. We therefore means angle R2 is equals to P1. Therefore, angle R2. It's a deduction. The moment you say therefore, you deduce from the above statements. From the above statements, we can then draw a conclusion that states angle R2 is equals to P1. Check at R2. Check at P1. With respect to APTR, R2 becomes an exterior angle and P1 becomes the interior opposite angle. Then you conclude that. Then we can conclude that APTR, therefore APTR is a cyclic quad. It's a cyclic quad. Why do you say it's a cyclic quad? Now you provide a reason. Why? Because the exterior angle is equal to the interior opposite angle. Because the exterior angle is equals to interior opposite angle. And once the exterior angle of a quadrilateral is equals to the interior opposite angle, then we know that that quadrilateral is cyclic. Interesting. Thank you. Every time, if I have to take you through the problem again, 4.2, prove that APTR is a cyclic quad. Ask yourself a question, when? Once you can answer that question, when, it gives you a direction. Then you know, I am working in this particular direction. This is the objective that I want to achieve. Now, in this case, we wanted to prove that R2 is close to P1 because we knew that if R2 and P1 can be equal, then APTR will then be a cyclic quad because the exterior angle will then be equal to the interior opposite angle. Just have to do lots and lots of exercise. Remember, as a grade 12 learner, you need to practice mathematics more often. And through practice, it will then become perfect. That's why I'm just taking you through this practice session. We are now practicing Euclidean geometry because we know very well that this coming test on Monday will also contain Euclidean geometry. Next one.